We'll wait for a couple of more minutes and then begin. Okay, let's begin. Hello, everyone. This is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So let's go over the questions of week 10 and then the contents of week 11 to help you solve the assignment. Okay, so these were the data given to you for the series of questions of week 10 assignment. So yeah, so for an aircraft, the tail area, we had done a question very similar to this in the last session. So it should have helped you with these questions. Okay, so for an aircraft, the tail area is 1/4 of the wing area and wing and tail are rectangular in shape. In addition, following data is applicable. So you have the weight of the aircraft, the cruising velocity, density at sea level, CL alpha of the wing, CL alpha of the tail, CMAC of the wing, uh, zero lift angle of attack, mean aerodynamic chord, span, and other geometric parameters. Okay, now let's look at the questions. First question was the location of neutral point in meters of the above aircraft from the leading edge of the wing. So we know the formula for neutral point. So we know it's split up, right? So I had said it was like a weighted average. So let's try doing that. So you have XNP is equal to CL alpha of the wing, CL alpha of the wing. Then you have XAC of the wing. So this is for the wing. Now let's look at the tail. You have eta tail ST upon S 1 minus dou epsilon by dou alpha. What else? CL alpha tail and XAC of the tail divided by the weights, right? So CL alpha wing plus eta tail ST upon S 1 minus dou epsilon by dou alpha CL alpha of the tail. So if you substitute all the data is given to you in the question, just substitute and find out the answer. You'll be able to get it. All right. So other things that you need to calculate here is dou epsilon by dou alpha. We know this formula. What is the formula? So it's 2CL alpha wing by pi E AR, where all terms have to be in radians or per radians. Okay, only then this formula is valid. And according to whatever is given to you in the question, you need to convert it. Okay, is there anything else? Yeah, AR we know is B square by S. Since it's a rectangular wing, you have B square by B into C, and you have B by C. That's given to you. Anything else? No. Okay, let's look at the next question. The total lift curve slope of the aircraft in per radian will be. So it's just the denominator of the weighted average. So it's the sum of the weights, right? So total lift curve slope, CL alpha wing, the denominator of the previous case, CL alpha. So it will be CL alpha wing plus eta tail ST upon S 1 minus dou epsilon by dou alpha CL alpha of the tail. Again, you have already calculated the denominator in the previous question. That exactly is the value here. Then, with static margin of 0.15, what is the total moment curve slope? CM alpha they've asked you. So we know that static margin is minus dCm by dCl. Now, if you just manipulate this a little, again, we've done something similar in the last class. dCm by d alpha into d alpha by dCl, and then you have minus Cm alpha by Cl alpha, and then you're required to find Cm alpha. So Cm alpha is nothing but minus static margin into Cl alpha. So you have minus static margin is 0.15. Cl alpha you calculated in the previous question. It's 5.917 and you get 0.887. All right. Okay, next question. With the static margin, same static margin, with a static margin of 0.15, what will be the location of center of gravity of aircraft in meters from wing leading edge? How will you do this? Static margin is the same, right? So what do? You write down static margin is x bar NP minus x bar CG. And they've asked you to find out CG. X bar NP you have, static margin you have. So x bar CG is x bar NP minus static margin. And you just need XCG, not x bar CG. Okay, so you have XCG is X NP minus static margin into C bar. X NP, what we calculated in the previous question. What was X NP? Okay, what was the value? X NP was 0.2 by C 0.2 minus static margin is 0.15 into C bar is 0.5. So you get around 0.125 meters. All right. Okay. What will be the horizontal tail volume ratio of the aircraft? What is the formula? VH. ST upon SC bar into LT. LT is the moment arm, which is X bar AC of the tail minus X bar CG. So you have 1 by 4 because here it says 1/4, right? And then C bar you have 0.5. Okay, you have X bar AC of the tail is 1.2, which is given in the question. Minus X bar CG, we calculated in the previous question. It's 0.125 divided by C bar. C bar is 0.5. So you get a value of around 0.537. Okay. Okay. What is the total pitching moment coefficient at 0-degree angle of attack? How do you do this? How do you proceed with this? So we have done this several times before. Cm naught is Cm naught of the tail plus Cm naught of the wing, right? So Cm naught of the tail is, you have eta tail St upon S, one, you have CL alpha of the tail and then the angles, right? So you have wing setting angle minus tail setting angle plus epsilon naught. When Cm naught of the wing is CMAC of the wing plus CL naught of the wing into X bar CG. X bar CG minus X bar AC. So you have something similar here, X bar AC tail minus X bar CG. Now all these quantities are known to you. What is not known? Epsilon naught. That is 2 CL naught of the wing by pi E AR. AR we had calculated previously. CL naught of the wing, you draw the lift curve slope and you should be able to find out, right? So this is given to you as minus 2 degrees. CL alpha of the wing is 5.5. So CL naught wing is, what does CL naught wing be? So 2 into 5.5 and it is in per radian. So you have to divide it by 57.3. So that's that. All the other quantities are given to you in the question directly and you can solve it. Then, what is the total lift coefficient at 0-degree angle of attack? CL naught. Again, contribution of the lift tail and a wing. CL naught of the wing, the CL naught of the tail. CL naught of the wing is nothing but, you already have the value, we've calculated it here. This one, right? Plus CL naught of the tail will be eta tail ST upon S CL alpha tail wing setting angle minus tail setting angle plus epsilon naught. Right? So this is the final answer. All right. Let's look at the questions for week 11, like concepts for week 11. What is aspect ratio from the given data? You can do this quickly, just try solving it quickly. Okay, so I hope you've been able to do this. It's very simple. So what do you do? So this value, you just equate the equation to the drag polar is equal to CD naught plus K CL square. So K is nothing but 1 by pi E AR. And you've been asked to find out aspect ratio. So AR is K pi E. K is 0.03 pi and E is 1. So what is the value? Just multiply it and let me know what the value is. Comes to 10.6, right? So that is the right answer. All right, let's go to the next question. What is the downwash angle if CL naught of the wing is given and aspect ratio is given? Direct formula substitution, right? You should be able to do this. Let's find out epsilon naught and both, right? Both of them, just do it both. Epsilon naught, dou epsilon by dou alpha. Let's take a couple of minutes and solve both. Okay, so it's a direct formula substitution. Epsilon naught was to CL naught of the wing by pi e a r. Okay, so pi e, this is given to you, AR is given to you, just substitute it. So you have 2 into 0.361 by pi, E assume it to be 1 and 7.1. What is the value? You're getting 0.0323. Okay, so if you had to do dou epsilon by dou alpha, you needed CL alpha value. 2 CL alpha win by pi E A R. Okay, and everything has to be in per radians. Okay, per radians. Per radians or radians. And the CL alpha wing is 3D. How do you relate it to the 2D? You have CL alpha 2D by 1 plus CL alpha 2D by pi E A R. Okay. All right. Now let's go to the next question. What is neutral point location if static margin is 0.12 and CG is located at 26% of the chord from leading edge? Very simple. Directly, everything is given to you directly. You just have to find out the CG, a neutral point location. Quickly, just do it. there was some technical problem. Let's continue here. So a static margin, very simple formula was x bar np minus x bar cg, right? Static margin is given to you as 0.12. You need to find out x bar np, x bar cg is 0.26. And the union percentage of chord, right? So you just have to subtract these two values, and what do you get? You get 0.37. It's closest to 0.38. All right. Next question. A wing is made of negative cambered airfoil. The lift coefficient at 0-degree angle of attack will be. What will it be? It's negatively cambered. So you have the lift curve slope. For symmetric airfoil, it's this. This is CL versus alpha. At 0 degrees, your lift is 0. Positively cambered, you have this, right? So at 0 degrees, you have a positive CL value. Negatively cambered airfoil, at 0 degrees, you'll have negative value. All right? Okay. Next question. The aspect ratio of an airfoil is, what will it be? Aspect ratio of an airfoil. What is the formula for aspect ratio? V squared by S. And now the S of an airfoil is infinite. Right? The span is of infinite span, so this will be infinite. Correct? So infinite. Okay. Which of the following statements are true? Read the statements carefully. Take a minute or two to read it and tell me the answer. Just take a minute or two. Alright. So airplane with higher wing loading has higher stall speed. What is the equation for stall speed? 2W by S rho CL max. Higher wing loading has higher stalling speed, right? So this is true. A low wing with dihedral contributes towards longitudinal stability. We had seen this, right? Low wing with dihedral contributes towards stability. That is true. A high wing contributes to lateral stability and longitudinal instability. The lateral stability we had seen multiple times. So um, this was high wing, and when it is subjected to a disturbance, it has a component of velocity, oncoming velocity acting in this manner, which produces a restoring moment, right? As opposed to a low wing. So low wing in the same direction would have a normal component of velocity acting here, and it will contribute towards further destabilizing the aircraft, right? So high wing is laterally stable. This we know. What about longitudinal? I think we had seen this during one of the weeks. So if this is your fuselage reference line and you have a high wing is like this. You have one lift component and one drag component, right? And your CG is here. Now, the lift and the drag, both of them produce destabilizing moments about the CG. Now, if you had a low wing, if this was your low wing, you had lift and you had drag, and you had CG here. The lift would produce destabilizing moment, but the drag would produce a stabilizing moment, right? Some stabilizing torque would be produced over there, but the high wing configuration produces unstable torque. So it produces instability, contributes towards longitudinal instability. Okay, so this point is also true. Winglets contribute towards minimization of wingtip vortices and thereby induce drag. This is true. We had seen in the first initial 2-3 weeks, we had seen this multiple times, that what causes vortices? The velocity that flows below the surface of the wing and above the surface of the wing, they interact at the tips. And when they interact at the tips, large vortices are formed. Now, when you introduce wing tips, the magnitude of these vortices are reduced and hence they induce drag. So all 4 points, all A, B, C, D are true. Okay, let's go to the next question. A wing is made of symmetrical airfoil. Lift coefficient at 0-degree angle of attack will be. We just saw this, right? It will be 0. We just saw this. So symmetric, positively cambered, negatively cambered. This is positively cambered, symmetric, negatively cambered. This is CL versus alpha. For symmetric airfoil at 0-degree, it is 0. Okay. The excess power of the aircraft determines what? What is the excess power of the aircraft? So excess power is power available minus power required. Do you remember where this term comes into play? It's the rate of climb, right? So rate of climb is nothing but thrust minus drag by W. Now, if you multiply it with the free stream velocity, it gives you power available minus power required by weight. Right? So rate of climb is the right answer. Next, a small UAV with a total weight of 12 kg is flying with a velocity of 70 meters per second at sea level. Wing area is 1.1 square meter. Find the lift coefficient. Try doing this again. Very simple question. Try doing this. So it's fairly simple. So you just have to find out the lift coefficient. What is the equation for that? 2W by S by rho V square. And you have 2W is 12 into 9.81 by S is 1.1. Density is at sea level, so 1.225 and 17 squared. Right? So if you solve this, you get it as 0.604. The next question. In a flight test, following data was obtained while trimming. Oops. Okay. Yeah. In a flight test, following data was obtained while trimming the airplane at different speeds. So see the data that is given to you. You have different speeds. You have the various angles of attack, CL at those values, and how much elevator was required to be deflected to trim the aircraft at the given CL, and the location of center of gravity at the different test conditions. Okay, and they give you a lift curve slope of 0.1 per degrees. Okay, now let's look at the series of questions. First one, what is the value of stick fixed neutral point? I think we've done something similar in the last week, so you should be able to do this. Try doing it. Stick fixed neutral point. Remember what data is given to you, and you can try drawing a graph to find out. They're giving you 4 sets of readings. Okay, try doing it. A hint is that you should be using the delta E required equation, right? So delta E required is delta E naught plus d delta E by dCl into CL trim. So apply it at all points and then find out the value of neutral point. So for each point, write this equation down, solve the equations, and find out the value of neutral point. So let's try doing this. We write the equation for each of those points. Now how do we get the xnp part of it? If you expand this, let me write it here. Delta E required is delta E naught plus x bar np minus x bar cg by cm delta E, right, into CL trim. Now write this equation for each of those points and then try to find out x bar np. I think there are 3 unknowns, right? So you have 1, 2, 3, 4. There are no, just 3 unknowns. You have delta E naught you don't know, x bar np you don't know, cm delta E you don't know. You will have 4 equations and 3 unknowns. You should be able to find out x bar np. So let's write it for the first one. Okay, so delta E required is 3 degrees up. Up is, our convention is elevated deflection downward is positive, upward is negative. So you have minus 3 equals delta E naught plus x bar np minus cg is 0.3, right? 0.3 cm delta E into CL trim is 0.5. This one. This is the first equation. Now let's write it for the second point. 1 degree upwards. So minus 1 is delta E naught plus x bar np minus 0.3 by cm delta E into 0.3. Okay. Now let's just try solving these 2 equations to get another equation. So just subtract them. Subtract the second equation from the first one. What do you get? This 0.3. Okay, what do you get? Here you'll get minus 3 plus 1 is minus 2. Oh, it's one degree down. So it should be plus 1. This is down. So you get minus 4 here. All right. Correct me if I'm going wrong. And you have x bar np minus 0.3 by cm delta E. These are the common terms. And you have 0.5 minus 0.3. Okay. So what do you get? You get minus 4. Or if you just write it in terms of x bar np, you get it as 0.3 minus 0.2 cm delta E if you solve it. Okay, so this is one equation. Now let's try it using the other 2 points. Okay, so the other 2 points are, you have 0 equals delta E naught plus x bar np minus x bar cg is 0.4 by cm delta E and CL trim is 0.4. Then you have 1.5 downward, so it's plus delta E naught plus x bar np minus 0.4 by cm delta E into 0.1. Again, solve these 2 equations and you get minus 1.5 plus equals x bar np minus 0.4 by cm delta E into 0.4 minus 0.1 is 0.3. And you get your x bar np equation as 0.4 minus 5 cm delta E. Okay. So now you solve these 2 equations to get your x bar np. If you solve it, you get x bar np as 0.433. So this is how you calculate values from experimental data. You can also just plot it and try finding it out. But since you have the data, the points are given to you directly, you can just use these equations and find out. Okay. Next question. Most aft location of center of gravity such that the aircraft has a minimum stability margin of 5%. You have the neutral point. You've given the stability margin, most aft center of gravity location. Very simple, right? Just try doing it. Quickly do this. I'll just give you a minute. So let's just do this quickly. Static margin is x bar NP minus x bar CG. Static margin is given to you as 0.05. X bar NP was 0.433 minus x bar CG. So that is your most aft center of gravity location, 0.383. All right, next. Most apt center of gravity location such that aircraft has minimum stability margin of 10%. It's just stability margin has changed, that's all. Let's try doing it. So it will be 0.1 equals 0.433 minus x bar CG. So x bar CG would be 0.333, correct? All right. Next question. Okay, so this is not from the series. For a conventional aircraft, the sign of CL delta A, CN beta are respectively. Now this I think we have done considerable amount of times. Try doing this, tell me. Let's just try finding out the signs of all these stability derivatives, okay? So let's just do it. Cm delta E, what do you have then? Cn delta R, and you have Cl delta A. Then these were the control derivatives. Now let's do stability derivatives. You have Cm alpha, Cn beta, and you have Cl beta. What should be the signs of all these quantities? Before that, let's see conventions. So deflection of elevator down, delta E, downward is positive. Then beta was, so this was positive, right? This is your fuselage reference line. And this beta is positive. So beta with velocity to the right is positive. What else? Delta delta R, rudder deflection towards the left is considered positive, right? Then anything else? Yes, delta A. What was it? Right wing upward, left wing downward, right? Right wing down. So right aileron up, left aileron down. CL beta will be less than 0. Now look at the control derivatives. If I deflect my elevator down, does it produce positive or negative pitching moment? Negative, right? So this will be negative. If I deflect my rudder to the left, does it produce positive or negative yawing moment? Negative yawing. If I deflect my ailerons in such a way, so positive is defined that right aileron upward, left aileron downward. That means it rolls with the right wing down, right? The lift on the right wing is less, so the right wing goes down. So is that a positive rolling moment or negative rolling moment? Positive rolling. So these signs you need to remember. You just need to remember the conventions and then you'll be able to derive the stability and the control derivative sign by yourself. Okay, next. Okay, look at the data that is given to you in this graph. Has it not loaded? All right, yeah. So aircraft total weight is 1,245.75 kgs. And the wing area is 17.075 meters square with the center of gravity position in ratio of mean aerodynamic chord, that is x bar CG, is given to you as 0.3. And so these are the graphs that are given to you of CM versus CL. So this is CM and this is CL. CM versus CL, negative slope, yes, and 0 or positive y-intercept. Okay, now look at the questions. Find the stick fixed neutral point. How will we do this? Take a minute or two to solve this. Let's try doing this. So what is the static margin? Static margin is defined as minus dCm by dCl, which is x bar NP minus x bar Cg. Now, x bar Cg is given to you. Static margin we can find out using the slope, right? So we just have to find the slope of any line. All those lines have the same slope, different intercepts, but the same slope, right? So pick any line. Let's take the first line. So let's take this point and this point. Okay. So what is minus dCm? So before that, we need to check the scale, right? So just see, let's look at this. Look at this point. So we need to get the y scale, right? So y scale is minus 0.15 minus of minus 2, minus of minus 0.2. And how many divisions are there in between those 2 points? 5. Right? So you have 1, 2, 3, 4, 5. So the scale is 0.01. Correct? So this quantity here will be, what will it be? It will be minus 0.15 minus of, there are 3 divisions there. So 3 into 0.01. What do you get? Minus 0.18. So the value of Cm at that point is minus 0.18. Okay. So put it here. You get, at this point it's 0. At this point it's minus 0.18. So 0 minus of minus 0.18. What about lift? It is 1.2. It's 0 minus 1.2. Correct? So what is the slope here? And it has a negative sign. So you get 0.15 equals x bar NP minus x bar CG. Now, x bar NP is 0.15 plus x bar CG is 0.3. So the answer is 0.45. Correct? So that is the value. Next question. Most aft location of center of gravity. What will it be? Most aft location of center of gravity. What is the most distant? How far can the center of gravity go before the aircraft becomes stable? As the definition neutral point, right? So it will be the value of neutral point, 0.45. It is neutral point, x bar NP. X bar NP is the aftmost that the CG can travel before the airplane becomes unstable. If a pilot wants to fly at a speed of 38.52 meter per second in trim condition, what will be the trim lift coefficient at sea level? They've asked you for CL trim. CL trim. Try doing this. It's very simple, right? You don't even need the graph for this, just do it. CL trim, what was the formula? At trim, what happens? Lift equals weight. So lift is half rho V square SCL. At trim, you can write it as W is half rho V square SCL trim. And they've asked you to find out CL trim. CL trim is 2W by rho V square S. Correct? So W here is 2 into 1245.75 into 9.81. It's being written. Yeah. Density is at sea level 1.225. They're giving you sea level here. Velocity is 38.52 squared. And surface area, wing area, 7.075. Just calculate this value and that will be your answer. Just calculate it. Comes to about 0.787. Okay, so that is CL trim. Very simple. Next, if a pilot wants to fly at a speed of 34.2 meter per second in trim condition, what will be the elevator deflection required to trim the aircraft at sea level? Try doing this. So just, we need to find out CL trim for the new trim velocity. So just do the previous, similar to the previous question, find out the CL trim. So CL trim is 2W by rho V square S. Find out CL trim and then find out the delta E required to trim at this CL. You know the delta E required formula, just plug it in and try doing it. How do we do this? How do we do this? So the value that you get here is around 0.999, which is about 1 degree. One, right? Not degree. 1. So now there are two ways to do this. Okay, so one, you can use directly the graph, draw two straight lines, draw a straight line at 1, right? And then draw it at 0. Okay, and where do they intersect? They intersect along the red line. And what is the value? What did they ask you? They've asked you, yeah. So that red line corresponds to 15 degrees, right? It corresponds to 15 degrees. So the value is 15 degrees, delta E required. Now, this can be a little, uh, there could be some error, right? So how do you do it otherwise? You take DCM by DCL. Okay, so what do you do? CM1 minus CM2 by CL1 minus CL2. Okay, and the 2 points you take, right? So the 2 points that you take are, let's write this down. So CM equal to 0, here CM equal to CM naught. What happens here? Here CL will be equal to CL trim at CM equal to 0, your CL is equal to CL trim, right? And when your CM is CM naught, your CL is 0. Okay, so basically you're trying to find out the slope and the intercept of the line, and then you match it. Slope will be the same, slope of all the lines is same, only the intercept changes. So you're trying to find out which intercept corresponds to which CL trim. Okay, so put it here. CM1 is 0, CM2 is CM naught, CL1 is CL trim, which is 1, we've got 1 here, and CL2 is 0. And DCM upon DCL we already have. Oops. The value is minus 0.15. So from here you get CM naught as 0.15. Now look at the intercepts here. So which of these lines have intercept of 0.15? The red line. Again, you get the red line as 15 degrees. Okay. So these are two ways to find out what is the delta E required when the graph is given to you. Next question. If suddenly the weight of 15 kg payload is dropped in flight and pilot wants to fly at same speed, 34.2 meters in trim condition, the elevator deflection required will be more, less, remain the same, or you cannot say. So what will change here? CL trim will change because your W is changing, right? W changes, CL trim changes. Now, W has reduced, right? So CL trim, the new CL trim is, let's just try doing it again, 2W by rho V square X, you get something around 0.987, which is less than the one value that we had gotten last time. So CL trim is less. Now write down your equation again. DCM by DCL, what was it? 0 minus CM naught. 1 minus 0. It won't be 1, it will be 0.987 minus 0 is minus 0.15. Then your CM naught value here will be around 0.14. So CM naught value is lower, right? So it's somewhere here. So now look at the trend of the lines here. When the CM naught is less, delta E is also less. So delta E required to trim the aircraft for a lesser mass will be less. We require less deflection of the elevator. All right. Okay. Next question. Next is another series of questions. Using the following information, answer the following questions. Okay, so you have a series of questions here. So read the data that is given to you. Aircraft type is civilian aircraft with pure turbojet. Then the mission is shown here. It takes off from point 1, climbs to point 2, cruises till point 3, loiters till point 4, again cruises, again loiters, again cruises, then lands. Okay, so that is the mission given here. It's flying at a Mach of 0.6, carrying 10,000 pounds of equipment, 4 crew members at 800 pounds. Aircraft loiters between 0.3 and 4 for 2.5 hours and 5 and 6 for 30 minutes. Consider L by D max is 16. Okay, so here it's a civilian aircraft with pure turbojet. This is the aircraft here. Find the weight fraction between 0.2 and 0.3, that is W3 by W2. Try doing this. What was the equation for weight fraction when the range is given? Point 2 to point 3, it's a cruise, right? So the range is given. So what was the equation? W3 by W2. What was the equation? Exponent of minus R C. So let's erase that. V infinity L by D max, or L by D, right? Where C is the specific fuel consumption in per degrees. Assume this is in per hour, okay? So this is in per hour. Okay, try doing it now. So how will we do this? So first of all, R range is given to you. That is 10,35433 feet. Okay. Next, what we need to find out, specific fuel consumption in per second. So what do? 0.9 by 3600, and you get 0.0025 per second. Next, you need velocity. They've given you Mach number. So velocity by speed of sound is Mach number. So velocity is Mach number is 0.6. Speed of sound in feet per second. Okay, because all the other quantities are given in feet per second. So just take feet per second. So the value is 994.8. When you multiply this, you get 596.88 feet per second. Then what is the next thing? L by D. So L by D for the turbojet, what was it? It is 0.866 by L by D max. Right? We had studied this ratio. So you have 0.866 L by D max is given to you as 16. How much do you get that as? You get 13.5856. Substitute all the values and find out W by W3 by W2. What do you get? You substitute all the values and you get 0.969. So that's this. Next question. Find the weight fraction between points 3 and 4. Points 3 and 4, the endurance is given to you, right? It's a loiter. Correct? So what is the formula for there? For the range case, for the cruise, we had the previous formula. For this, you have W4 by W3 is exponent of minus endurance times specific fuel consumption and L by D max. Correct? Now try doing this. 2.5 hours into 3600 because you need it in seconds. So it comes to 9,000 seconds. Substitute all the values. You get W3, W4 by W3 as 0.88. All right. Okay. Along similar lines, find the weight fraction between 0.4 and 0.7. How will we do this? It's between multiple points, right? So what do you do? Find the weight fraction of individual segments and multiply them. So you need W7 by W4. What you do is you do W5 by W4 into W6 by W5 into W7 by W6. Find out the weight fractions of individual sections and multiply them together. So let's find out W5 by W4, that is cruise. So your equation was minus RC by V L by D, right? Find that out. And then you have W6 by W5. What is that? That is loiter. So you have E raised to minus endurance times C by L by D max. And then you have cruise again. Cruise again. W7 by W6 is E raised to minus RC by L by D. Just find out these terms and multiply it. Try doing it. I'm getting 0.939. Verify these answers, okay? Just verify them. This is 0.975 and this is 0.939 again. Both those cruises, okay. By doing it and verify those answers, tell me if they're right. Both the cruises are for the same range, so your ratio for both the cruises is the same. Now just multiply it. You have 0.939, 975 into 0.939. You get value of 0.889. Or 859. Correct me if I'm going wrong, okay? So 0.859. All right. The last question, weight fraction between 0.6 and 8. Try doing this by yourself. It's similar to the previous case. Try doing this. It's last question for this session. Just do it. This was the last question for today. I think it's fairly simple. W8 by W6 is W7 by W6 into W8 by W7. W7 by W6 we have already done. We need to find out W8 by W7, right? Along similar lines, what will be the formula? Is 0.995. There is no formula, it's given to you directly, right? 0.995. Just multiply these two and you should be able to get it. So that was, what is W7? Okay. 939 into 0.995. You get the value as 0.934. So with this, I think you should be able to understand how weight fractions are calculated when such mission plans are given to you. So if there are no questions, we can end the session here. All the very best for your test tomorrow. We'll meet again next Tuesday. Thank you.